Imagine your company just spent, I don't know, $2 million on this state-of-the-art impenetrable security gate for your corporate headquarters.
Oh yeah, like retinal scanners, armed guards, the whole nine
Right,
yards.
exactly. And you feel completely secure. But what you don't realize is that an attacker bypassed the gate entirely by just, walking through a side door disguised as a delivery driver.
Yeah, happens all the time.
And now they are currently sitting in your break room, mapping out the entire building from the inside. Today, we're looking at how modern enterprise networks fight back against those exact
It's a
scenarios.
huge issue, yeah.
Welcome to today's mission. We are taking a comprehensive, highly methodical deep dive into the network security and architecture concepts covered in the HPE7-A10 exam.
And look, we are going to take our time here.
Yeah, we're adopting a deliberate, really measured approach today because understanding this, well, it isn't just about passing a test. It is about understanding the invisible digital bodyguard systems working around you every single day.
It is so crucial to slow down and really dissect these mechanisms. I mean, modern network architecture is incredibly complex.
Absolutely.
It isn't just about moving data from point A to point B anymore. We are talking about dynamic security, split-second trust decisions, and automated containment.
Right, all happening entirely behind the scenes, right?
Exactly, often in like fractions of a millisecond. If we don't understand the underlying why and how, the whole system just looks like magic.
So whether you are currently prepping for the HPE7-A10 exam, or you are just insanely curious about how enterprise networks actually keep hackers out in real time, this deep dive is going to decode it all for you.
Yeah, we've got a lot of ground to cover.
We have a stack of 10 specific scenarios to analyze sequentially, so let's get right into it with the very first line of defense, figuring out if the device at the front door is actually allowed inside. Question 1. An enterprise network must verify client certificates in real time without downloading large files. Which service provides this immediate verification?
The correct answer is A. And, the reason this trips people up on the exam is because of the sheer scale of modern networks. This tests real-time certificate status checking using the Online Certificate Status Protocol, or OCSP.
OCSP.
Yeah. When a device presents a digital certificate to connect, the network has to know if that certificate has been revoked.
Makes sense.
Historically, networks used certificate revocation lists, and those were massive text files containing every single bad certificate.
Like downloading a whole novel just to check one word.
Exactly. OCSP changes the game by querying the status of just that one specific certificate in real time, determining if it is valid, revoked, or unknown without downloading the massive list.
Think about a bouncer at an exclusive club. Using OCSP is like that bouncer quickly scanning a VIP list on a tablet, right?
Oh, that's a great way to look at it.
They instantly ping the central server to see who is allowed in right at that exact second. The alternative would be forcing that poor bouncer to read the entire city's printed phone book before deciding if they can let someone inside.
Right.
It creates unacceptable latency.
Right, and if that bouncer's tablet goes offline, or, if the process takes too long, the whole line stops.
Yeah, total bottleneck.
And that is the critical vulnerability in enterprise access. The authentication server has to make incredibly fast trust decisions, often while a user is just, like, walking down a hallway seamlessly transitioning between wireless access points.
No, yeah.
You literally cannot afford to wait even 3 seconds for a security check. So OCSP streamlines that cryptographic verification into a rapid, lightweight query.
But that reliance on verified identities assumes the device is playing by the rules, right? We have to consider what happens when a device is actively trying to hide its identity from the network.
Yeah, the rules have completely changed recently.
Over the last few years, major smartphone manufacturers completely changed how devices broadcast themselves for privacy reasons. That creates a massive blind spot, which leads us to question 2. Traditional device identification fails when smart devices randomize their hardware addresses. How can modern visibility tools accurately classify these unknown devices?
The correct answer is B.
Got it.
Looking closely at this, it's a direct response to a massive shift in mobile operating systems. Because smart devices now randomize their MAC addresses to prevent tracking in public spaces, well, traditional visibility tools fail.
They just can't track them anymore.
Right. So to compensate, modern tools must analyze traffic patterns, protocol behavior, and communication characteristics to accurately classify unknown IoT, BYOD, and unmanaged devices.
So when a device randomizes its hardware address, it is essentially like someone wearing a disguise.
Yeah, a digital disguise.
If they change their face every time they walk into the building, how do you recognize them? Well, the network has to stop looking at their ID badge and start analyzing their behavior.
Exactly.
Like, how do they walk? How do they talk? Who do they talk to?
Exactly. We call it behavioral profiling. Let's say a device connects with a completely randomized, unrecognizable MIC address. The network controller just watches what it does.
Just observes it for a bit.
Yeah. Does it send out an HTTP request with a user agent string claiming to be an Apple TV? Does it request an IP address using specific DHCP options unique to an Android phone?
Oh, I see.
Or maybe it acts exactly like a smart thermostat, pulling a highly specific weather server on port 443 every 5 minutes. The network analyzes those behavioral fingerprints to classify the device, regardless of the disguise it is wearing.
Okay, so we successfully identified the disguised smart thermostat using behavioral profiling.
Right.
The next logical step is wanting to deeply inspect its traffic to make sure it hasn't been hijacked by malware. But here's the problem. A lot of corporate buildings are running on edge switches that are 10 years old.
Oh, yeah. Totally physically incapable of advanced deep packet inspection.
And replacing them all would cost millions.
Millions.
This introduces question 3. A network team wants to apply deep packet inspection to wired clients without upgrading edge switches. Which architecture achieves this goal?
The correct answer is C.
Okay, so how does this work?
The operational reality here is about preserving capital expenditure, User traffic is tunneled from the wired edge to a central security gateway for firewalling, application inspection, and policy enforcement, leaving existing edge switching infrastructure entirely in place.
To visualize this tunneling concept, imagine a sprawling metropolitan city.
Okay.
Upgrading every single local train station on the outskirts of the city to have a state-of-the-art TSA-style security checkpoint would be an absolute nightmare, right?
Oh, impossible.
So instead, you build a dedicated express subway line. When someone gets on at the edge of the city, they're put into an express tunnel that bypasses all the local infrastructure.
Right.
It takes them straight to one massive, high-security checkpoint downtown.
That is precisely how network tunneling works technically. The older edge switch takes the user's data packet, wraps it inside another protocol like a GRE or IPsec tunnel, and essentially blindfolds it.
So the edge switch doesn't even look at what's inside?
No, the edge switch doesn't need to analyze the data at all. It just forwards the encapsulated package directly to a highly intelligent central security gateway.
Ah, the downtown checkpoint.
Right. That central gateway strips off the tunnel, performs the heavy computational lifting of deep packet inspection, and enforces the security policy. You get modern security without ripping out thousands of physical ports across your campus.
That's brilliant. So we've got the perimeter and the edge tunneled perfectly to a central brain. But what if the threat doesn't have to cross the network core?
Yeah, the insider threat.
Exactly. What if the call is coming from inside the house? Let's say a trusted internal server suddenly gets compromised and starts poking around the local network. Question 4. A compromised internal server begins scanning the network for vulnerabilities. How can embedded switch analytics immediately stop this activity?
The correct answer is D.
All right.
When we look at switch-level defenses, embedded switch analytics compare current traffic against normal baselines to identify abnormal vulnerability scanning, automatically applying restrictive policies to contain the compromised device.
Okay, I have to play devil's advocate here.
Sure.
Wait, so the network just automatically locks down a server if it starts acting weird. Isn't automated containment incredibly risky if the system makes a mistake?
It definitely can be, yeah.
Let's say a critical internal database just happens to have an unusual spike in traffic because of, like, an end-of-quarter financial backup, and the network automatically shuts it down. I mean, that is a massive, self-inflicted outage.
You are touching on one of the most hotly debated topics in network engineering right there. Automation carries severe risks.
Right.
That is why the mechanism here relies on deeply learned and normal baselines. We aren't just looking at raw volume. The analytics engine at the switch's hardware level. The ASIC is monitoring the types of connections.
Oh, so it's much more granular.
Way more. If a server that normally talks to 3 web servers suddenly starts rapidly pinging every single IP address in a 24 subnet on 100 different ports, well, that is the undeniable mathematical signature of a vulnerability scan.
That makes a lot of sense.
The risk of letting a worm spread laterally is far worse than the risk of a false positive. The automated response must act faster than a human ever could.
It is a calculated risk, relying on highly tuned telemetry. But, automated defense in a wired network is one thing. When you take automated containment to the airwaves, the Wi-Fi spectrum, you introduce a completely different set of physical and legal liabilities.
Oh, absolutely. It's the Wild West out there.
Which brings us to question 5. A security team enables automated containment to disconnect clients from unauthorized access points. What is the primary operational risk of this feature?
The correct answer is A. The physics of radio frequency is the core issue here, really.
Yeah.
Incorrect classification may disrupt legitimate wireless networks of neighboring businesses because wireless signals extend beyond company boundaries and require highly accurate rogue AP detection.
Wow. So if you misconfigure automated wireless containment, you aren't just securing your network, you are essentially deploying a digital jammer.
Yep, pretty much.
Imagine having an automated lawn sprinkler system designed to keep pests off your grass, but it is miscalibrated and it ends up shooting high-pressure water directly through your neighbor's open living room window. You are completely ruining their day.
And in the wireless world, ruining their day means actively breaking their network.
Right.
When a wireless intrusion prevention system, or WIPS, decides an access point is a rogue threat, it forcefully disconnects devices by spoofing unencrypted 802.111 deauthentication frames.
Wait, spoofing?
Yeah, it sends a message pretending to be the access point, telling the client to disconnect. But wireless space is shared space.
Oh, I see where this is going.
If your WIPS mistakenly classifies the coffee shop's Wi-Fi next door as a threat, you are actively launching a denial-of-service attack against an innocent neighboring business. The legal and operational fallout from that is immense.
Yikes. So to avoid having to aggressively shoot down rogue access points and risk hitting the coffee shop, enterprise networks need to guarantee their devices are connecting to the real network and not like a fake one set up by an attacker in the lobby.
Exactly. Prevention is better than containment here.
Question 6. A company is upgrading from password-based access to certificate-based security. What makes this new approach highly resistant to credential theft?
The correct answer is B.
Okay.
Passwords are fundamentally flawed because they can be stolen and replayed. Mutual certificate authentication requires both the client and the server to cryptographically prove their identities, eliminating the risk of attackers simply stealing or reusing a password.
The operative word for you to remember here is mutual. We are so used to one-way authentication. You type your password into a website to prove who you are.
Right, which is so easily spoofed.
But in a secure enterprise network, it is a secret handshake where the door also has to perform a complex cryptographic handshake back to you to prove it is the real door and not a fake portal designed to steal your credentials.
That mutual verification, typically using a protocol like EKP TLS, is the absolute gold standard of access security.
Gold standard, yeah.
The client device presents a digital certificate, which is a complex mathematical key pair that is infinitely harder to extract than a static password. But crucially, the network authentication server then presents its own certificate back to the client.
Okay.
If an attacker sets up a fake access point in the lobby, they will not possess the corporate server's private key.
Right.
The client's laptop will immediately recognize the cryptographic fraud and silently refuse to connect. The user is protected from their own potential gullibility.
It takes the human error out of the equation entirely.
Completely.
No more employees getting phished by a fake login screen. But think about the sheer volume of data this generates. With all these complex mutual handshakes, dynamic behavioral profiling, and automated containment actions happening thousands of times a minute across a global enterprise, the network generates mountains of security logs.
Mountains of them.
And those logs are completely useless without one foundational element. Let's look at question 7. Security analysts are unable to correlate security events across multiple access ports and gateways, which fundamental network service must be fixed.
The correct answer is C.
All right.
When you are analyzing a breach, well, time is everything. Synchronized network time, using NTP, is required, so events from access points, switches, and gateways have accurate timestamps. Without consistent time, analysts see the right events, but in the wrong order.
Imagine trying to solve a complex murder mystery. You have 10 reliable witnesses who saw different pieces of the crime, but every single witness has their watch set to a completely different random time zone.
That would be a nightmare for a detective.
Exactly. One says the suspect fled at 2 p.m., another says they broke in at 6 p.m., another heard a noise at 9 a.m. The detective would never be able to build a cohesive timeline. But wait, don't all these enterprise routers and servers just use atomic internet time automatically?
Well, you would think so, right?
Yeah. How does a $500,000 network just, lose track of time?
That is the great question. Networking hardware relies on relatively cheap internal quartz oscillators to keep time. Left to their own devices, these physical components drift due to heat, age, and tiny manufacturing
So
variances.
they just naturally get out of sync.
Yeah. One switch might run a few milliseconds faster per day than the firewall next to it. Over a month, they are seconds apart. When a security information and event management system, a SIEM, tries to trace a hacker's lateral movement, milliseconds matter.
I bet.
If the firewall says the attack happened at 12.000.01, but the edge switch says the payload was delivered at 12.00000, cause and effect breaks down entirely. The network time protocol ensures every device is rigidly synchronized to the exact same millisecond.
Wow. Time is the chronological glue holding the entire security narrative together.
It really is.
So we've built this highly orchestrated, perfectly timed, deeply inspected security apparatus at our central headquarters. The challenge now is extending it to remote branch offices without slowing everything down to a crawl. Question 8. A remote branch office requires secure internet access without routing traffic back to headquarters. How should the branch gateway be configured?
The correct answer is D.
Okay, lay it on me.
Historically, enterprise architecture relied on routing all remote traffic back to a central hub, but the modern approach is vastly different. The branch gateway establishes encrypted tunnels directly to a cloud security node where traffic is inspected, improving performance while keeping centralized policy enforcement.
So instead of forcing every remote employee's internet traffic to commute all the way back to the main corporate headquarters just to go through the primary security gate, which obviously causes a massive latency-inducing traffic jam, you route them via a secure tunnel directly to a cloud bouncer.
Yes. And the technical term for that traffic jam is hairpinning.
Hairpinning.
Yeah. If a user in a branch office in London wants to access a cloud application like Salesforce, and the headquarters firewall is in New York, routing that traffic across the Atlantic Ocean and back just for inspection is incredibly inefficient.
Right, so the solution is bypassing that commute entirely. The gateway at the London branch builds an IPsec tunnel directly to a cloud security node physically located in London.
Exactly.
That node applies the exact same strict corporate security policies as the New York headquarters would, and then lets the user out onto the internet quickly.
It is the foundational concept of Secure Access Service Edge, or SAS. You distribute the security enforcement geographically to the cloud edge, but you centralize the management and policy. However, regardless of where a user is located, a critical vulnerability remains.
What's that?
What happens if an employee passes all the mutual authentication, goes through the cloud bouncer, connects cleanly, but then plugs in an infected USB drive an hour later?
Oh man, you need a way to intervene mid-conversation. Question 9. An endpoint security agent detects a virus and needs to immediately isolate the connected laptop. Which protocol capability enables this mid-session network change?
The correct answer is A.
All right.
This challenges the old-school mindset of network access. Radius change of authorization allows a policy server to disconnect, quarantine, or reassign a device during an active session, isolating the malware immediately.
This should be a real aha moment for you. We often think of network authentication as a one-and-done event.
Right, like a ticket at a game.
Yeah, exactly. You show your ticket, you walk into the stadium, and you are good for the rest of the game. But modern zero-trust architecture doesn't work like that. It is continuous.
Constantly verifying.
The change of authorization, or CoA, is the digital equivalent of a security guard tapping you on the shoulder and physically escorting you out of a building long after you were initially allowed inside. But wait, how does the switch actually execute that command without dropping the physical link?
It's a fascinating mechanism, actually. The endpoint security agent on the laptop detects the virus and alerts the central policy server.
Okay.
But the policy server isn't the device actually routing the user's data. The local edge switch is. So the policy server fires a specific radius CoA packet to that edge switch.
So it tells the switch to do the dirty work.
Yes, it dynamically commands the switch to change the rules for that specific port. The switch might instantly tear down the user's connection and drop them into a restricted quarantine virtual LAN, completely severing their access to the corporate network, all while the physical cable remains plugged in. It happens midstream, without waiting for the user to log off.
Wow. It's immediate active enforcement. But as we reach our final scenario, we have to recognize a brutal reality. All of these high-level policies, the cloud nodes, the dynamic profiling, the CoA mean Absolutely nothing if the foundational routing logic of the physical network itself is tricked by an attacker.
The lowest level is always the most vulnerable.
Question 10. An engineer wants to prevent attackers from intercepting traffic by pretending to be the default gateway. Which security features prevent this deception?
The correct answer is B.
Okay.
Layer 2, the physical local network, is inherently trusting, which makes it incredibly vulnerable. DHCP snooping builds trusted IP to MAC address bindings, and dynamic ARP inspection checks messages against those bindings to prevent ARP spoofing and man-in-the-middle attacks.
To put this simply, it stops an attacker from standing in the middle of a busy hallway and shouting, "I'm the exit, everyone come this way." But what actually is ARP spoofing mechanically? Why would the network believe the attacker?
Because the Address Resolution Protocol, or ARP, was designed in the 1980s when everyone on a network just trusted each other.
Right, a much simpler time.
Very much so. Computers maintain an ARP cache, which is a small table mapping IP addresses to physical MC addresses. If an attacker sends a forged gratuitous ARP message claiming their laptop's MC address owns the IP address of the router, every machine on that switch blindly updates their cache.
Just believes them without checking.
Yes. Suddenly, all the traffic meant for the internet is flowing directly through the attacker's laptop. They become a man in the middle.
So they intercept everything. How does dynamic ARP inspection stop the lie?
It forces the network to check an unforgeable registry. When a device connects and gets an IP address, the switch uses DHCP snooping to secretly record exactly which physical port received which IP address. That database is the absolute truth.
Got it.
When the attacker tries to shout that they are the router, dynamic ARP inspection intercepts that message, checks the DHCP snooping database, realizes the attacker is lying about their identity, and instantly drops the malicious packet.
Preparing for the HPE7-A10 exam reveals that modern networking requires dynamic, centralized, and cryptographically verified strategies at every single layer. From real-time certificate checks to stopping local spoofing attacks, the entire system must continually assess trust and enforce policies without hesitation, because the moment a network assumes a device is safe,